You. Yeah, feel free to heckle along the way. So I'm Nick Rintalan. This is Dan Allen over here. We're a couple of lead architects with Citrix Consulting. We're in the Americas Consulting organization. I'm based out west in San Francisco and cover a lot of the large accounts out there. And then Dan's based in Pennsylvania and covers a lot of our big accounts in the public sector space. Collectively, we've got about, I think, 22 years with CCS. So we're going to talk about why IOPS suck today, and they do suck. So let's kind of jump right in here. 1 trillion, billion, million IOPS. And I was working in my basement over the weekend, and I invented an array that can do 1 trillion IOPS. There, I said it. Somebody proved me wrong. It just so happens that I used 100% sequential I/O. It was all reads. I had a terabyte of cache, huge block size, and then it was 100 milliseconds of latency, nothing even close to 1 or 2, where you want to be. And also note this was peak IOPS only. This was an average IOPS. This was a single VM, not a lot of VMs to confuse the storage array. And this was like 1,000, let's say, parallel threads. So these are the kind of claims that are out there and why I want to talk about why IOPS suck, because I'll just say it. IOPS numbers by themselves are completely worthless. They're meaningless. And over again, we see storage vendors, we see consultants. I mean, we're guilty of it. Just saying these numbers like, we have an array that can do 1 million IOPS. Like, what the hell does that even mean? I couldn't even tell you. So if somebody gives you, if somebody's throwing out numbers like that again, like I said, slap them. I mean, don't slap them, but just ask them, for some clarifying info. What are you using in those tests, right? That's what we really want to talk about. So what's on tap? We'll do a quick overview, an IOPS refresher. This, we're not going to talk about some of the storage basics and stuff. We've been talking about this stuff for a few years now in the industry. So we're going to breeze through the IOPS refresher. And then Dan's going to give you a history lesson, why we started caring about IOPS, and show you some interesting field tests we've been doing with cache. We'll talk about all IOPS are not created equal, how storage vendors dupe use, one of my favorite sections. Any storage vendors in here? HP, NetApp, Hitachi? Come on, don't be shy. Nobody's going to raise their hand. Come on, really? All right. One brave soul. I'll try to be nice. And then we'll talk about some real-world stuff. So I want to show you some real-world, VDI and XenApp workloads and I/O profiles, really. So you can be equipped with what to ask, our storage vendors when they give you these ridiculous IOPS numbers in the millions. And then some conclusions and key takeaways as we wrap it up. All right. So typical consulting style, what's out of scope? We're good at this. So we're not going to talk about IOPS estimates. We've been talking about estimates, right, for last 3, I think, BriForums. So if you don't know by now what a Windows VM averages in terms of IOPS, or what a XenApp user averages, we'll talk about that a little bit. I mean, we have a couple stats, but we're not going to give you the nice pretty tables. There's a million guides out there all over the internet, so you can Google it. All right, quick overview, IOPS refresher. So let's start with what is an IOP? So basically, it's a measure of work versus time. That's kind of what it means to me. Common performance measurement, right, that storage vendors use and other folks use out there to benchmark storage devices, storage systems, storage arrays. Iometer, IOmeter, whatever we're calling it. That's I think probably the most popular tool out there to it's an I/O subsystem characterization tool. I think that's actually how they define it, but very popular tool, and there's a million others. The one formula I wanted to throw up here, though, is IOPS times block size. So the first really important point, block size. If nothing else, if you don't remember anything else, talk throughput, don't talk IOPS. Throughput at least gives us an idea of the block size. It takes that into consideration. IOPS doesn't by itself. So whether it's an 8K block, 4K block, 128K block, that plays into this formula. So real storage guys and gals, I was saying, they talk throughput. Megabytes per second, gigabytes per second. That's what we want to be talking, because at least it takes into account the block size. IOPS don't. And so here's like the SanDisk U100, just a sample here. This is actually like the SSD, the consumer grade SSD I have in my laptop right here. And just to give you an example, like what they show on their website, basically 450 megabytes per second. So that's a throughput number. They're talking IOPS there without saying it's 9,400 IOPS. Does that make sense? So that takes into account the block size. Yeah.
I guess is the subnote or the subscript there to a footnote that says what the block size that they're using is for that?
Yep. Yeah.
And it's the same kind of thing. It's just a throughput number. It doesn't tell you anything.
Yeah. They clarified. Actually, I think I have a picture on the next slide. Good point, though. You're right. So if they just give you this and they don't say anything, but usually in the graphs, you know, at least all the storage benchmarking tests, they'll have like the block size at the bottom if they're giving you a throughput number. It's surprising. I'll show you like the real storage vendor tests, and they don't. A lot of times the block size is unknown, or they're giving you an IOPS number and they don't say anything. So it's kind of ridiculous. So yeah, all IOPS aren't created equal. First we talked about, so there's read IOPS, there's write IOPS, there's sequential IOPS, there's random IOPS. Then there's, you know, the notion of average IOPS. There's peak average IOPS. There's, you know, peak IOPS. You know, these are all different too. So this is why it's kind of complicated. And, you know, basically the easiest thing to do, right, is a bunch of sequential reads. You know, that's where most of these numbers are coming from that the storage vendors will quote. They play to their strengths, but more often than not, they're going to probably use, you know, something like 100% sequential read I/O, or maybe it's a mix of like 70% sequential read I/O and 30% random write or something like that. It's just always going to be on the high side of sequential reads. The other thing, large block size versus small block size, right? So the stuff we're going to talk about for like a VDI profile, that's more of the really difficult stuff. That's why people struggled for the last 3-4 years doing VDI deployments, because storage was, you know, we figured this out the hard way. You know, our I/O profile wasn't a bunch of reads anymore. You know, it's not a database application that we were virtualizing that was doing 66% reads. All of a sudden we flipped it on its head and it's 80% write IOPS, and they're random write IOPS, and they're 4K. So they're the nastiest, worst kind of IOPS, I guess that's what I'm trying to say. The other thing, so here's that picture I wanted to show you. So they actually quote, you know, they say now, you know, the 4K random reads, that's what they're using. And then the other thing with the notion of sustained IOPS. So see the difference there between I kind of gave it a bit. Anybody know the difference between like a consumer grade SSD and an enterprise, you know, flash drive, an EFD, like EMC? What's the difference between like an enterprise grade SSD and a consumer grade SSD? Yep, cost, but why does it cost so much more? Right, so mine's $200 and then these are, you know, 2,000 or, you know, 10,000. So yeah, it's write performance. That's the first one. So look at that, 1,200 IOPS versus 9,400 IOPS. That's what my drive can do. You know, if this was an enterprise grade flash drive, it'd be like 9,400, 9,400. The other thing is longevity. So, you know, my little guy here is gonna, you know, it's gonna burn out in like a year or two, right? They're not rated that high. Whereas like an EFD might be rated for 6 to 8 years of longevity. So that's what you're buying. Yeah, question?
SLC, is SLC faster than MLC? Not anymore.
Yeah, I think the lines are blurred there, and there's a million different, you know. Yeah, and they have their own strengths and weaknesses, right? So we could go all day on that. I wrote our SSDs, all they're cracked up to be a couple years ago. If you guys want to check that, Google that one. But it's an interesting read, talking about some of that stuff when SSDs were kind of new and just coming out. Oh yeah, so why is this so complicated? Again, we already talked about read, write, sequential random. You know, all IOPS aren't created equal. The block size. Another thing when we're doing these tests is, you know, how many VMs are generating the load? How many workers or how many threads? You know, in IOMeter, you can specify how many outstanding requests. Is it 16, 32, 1? The IOPS number is going to completely vary, yeah.
I think 16, basically because you get improvements in performance from 1 to 16 as you increase the number of outstanding IOPS. Over 16, well, you tend to get no improvement in IOPS, but you get extended latency.
Yeah, and I think 16 is actually the default they have in there for like the, you know, their basic profile, isn't it? Oh, really? I thought I was 16. I have a screenshot later. We'll check it out. I think I just had the default in there, but I don't know. I'm not positive. But yeah, it's funny though. So most of the tests you'll see later on, they do use 16. So that's kind of the most popular number out there. Seen some like VMware they use 32, but 16 seems to be the most popular. Thanks. Latency, you know, and this is what really, really matters a lot. So we talked about IOPS, work versus time. Latency is just time. So that's, you know, it's how long you're waiting. And we'll talk about what's a kind of a good sustained latency where we want to be. RAID type, so again, the notion of, I call them raw IOPS and then versus effective IOPS. So if somebody's quoting you, a 1 million IOPS, a storage vendor, it's like, is that just a raw number? What happens when you throw RAID 5 or RAID 6 down on it, or RAID 10? How does that change it? Does it cut it in half all of a sudden? Oh yeah, it does. Like, well, that would have been nice to know, like most people use RAID 5 and 6 and stuff out there these days. So I'll show you the next slide. I just got an example of what I mean. Cache. So Dan and I were talking before we walked in here. Cache is king. This is what makes a lot of the math really fuzzy too. So a typical disk, we'll say a spinning 15K SAS disk might give you 200 IOPS. Well, what happens if there's like a RAID controller in there, and the cache is say 50-50, tuned for 50 reads and 50 writes? What happens if it's tuned for 100% writes, 0% reads? What does that do to your IOPS number? Well, it changes it drastically. How much does it change it by? We're going to show you a real-world graph of what we did with that. But yeah, cache, and then it gets, so that's the easy example in like a single server host. What happens when you have an array, like a Hitachi array or an EMC array, and they have 128 gigs of global cache? I mean, who knows? New techniques like, auto tiering, dynamic storage tiering. So most of the big iron guys have their flavor of this, EMC fast, fully automated storage tiering, and Hitachi has like HDT, dynamic tiering. So there's that makes it more complicated, but basically there's the notion of using SSDs with SAS drives, with SATA drives, and based on the heat map, basically what IOPS are, hot or used the most or most frequently being generated, we basically tier those. Tier 0 becomes your SSD, tier 1 your SAS drives, tier 2 your SATA drive, or your SATA tier there. Yeah, and then the last thing that makes it so damn complicated is every vendor has their own notion of what they should be testing of all this stuff. So like Jim said, 16, it's like, yeah, that's what VMware uses, but Citrix doesn't use that. HP doesn't use that. And like, NetApp thinks a good, profile is 80% writes, 20%, reads for VDI, but VMware thinks it's 50-50. Citrix thinks it's different based on if you're using PVS and MCS. So this stuff's really complicated because everyone wants to do their own thing. And yes, there are like some storage councils out there, like Storage Performance Council, SPEC. They try to, kind of standardize on some of these variables here, but these guys just don't listen, and that's an independent thing. And so the vendors and they're just going to do their own thing no matter what, and that's what we'll take a look at some of those tests. So one quick slide on raw IOPS versus effective IOPS. So the RAID type really does matter, and this is how much it could matter. So it's all about the write penalty. In the case of VDI, if we're using PVS especially, we're just generating so many random write IOPS. So the write penalty is very important to understand. Whether you're doing RAID 5 or 6, and why we recommend RAID 10 is because the write penalty is 2. So it's, literally, and here's the example. This was from a real customer down in South America. I was visiting in Brazil. They just, they were short on spindles, but they just wanted to stay, with RAID 6. And 833 to 300, that's the difference. So don't just take the raw IOPS number, or at least question, is that a raw IOPS number, or what happens, when you put some RAID in place. Very, very important. All right, hand it over to Dan here. He's going to walk you down memory lane.
So how many people here deployed MetaFrame or presentation server on physical hardware back in the 2000s, say 2000 to 2008, 2007 days? All right, great. Most of you. So when you were doing that and you were speccing out the server that you needed to buy, right, trying to figure out how many users am I going to get on this HP box or on this Dell server, what did you really worry about? RAM. RAM was a big one. CPUs, right? Memory and CPU were the two big things. How many sockets? Am I going to use hyper-threading? Am I not? Am I going to buy a 2-socket server? Am I going to step up and do a 4-socket server? We never talked about IOPS. Did you ever have IOPS discussions when you were talking about sizing a presentation server?
One person right here.
What?
Office 2007.
Okay.
Destroyed our IOPS.
Destroyed them. Okay. So 2007, IOPS started becoming popular. But for most of us, we didn't think about IOPS. But what did we think about? The RAID controller, right? And what was the most important thing for a terminal server that we had to have? A write cache, right? Go ahead.
Gotta remember to put the battery in the thing.
The battery-backed write cache.
Yeah.
Exactly.
One of our old like CCS recommendations was like BBWC. I mean, we could rattle that off so quick. Battery-backed write cache. That's what it was all
And
about.
Microsoft even had an article, a Q article, that we reference so much, MS 324446. I'm sure most of you guys have probably read it out there. I've had to quote it to customers so many times, right? And that was the Microsoft article that had a lot of good information about registry tuning, but it also talked about if you want to have more than 40 or 50 users on a server, what do you need? You need caching. It said you need a RAID card with a write cache, or you can actually go in, if you don't have a RAID card, you can go in to the device manager, and what can you do? You can turn on write caching on the disks if the disks have a cache. Of course, if the server goes down, there's no battery there, so you would put your data at risk, which on a XenApp box really wasn't that big of a deal anyway, because hopefully you don't have any data on there. But we worried about write caches. We never talked about the IOPS number, but we knew that if a customer didn't have a write cache on the server, that at 40, this thing turn off? At about 40 or 50 users, we were probably gonna start to max out. So what did a typical server look like then? Did we have a lot of disks? Did we have a lot of IOPS? Well, a popular server model was to just put 2 disks in a RAID 1 array, right? So 2 SAS drives. Maybe you had 15K SAS. I know a lot of the deployments I did to customers, budget was a concern, so they'd put 10K SAS drives in there. Now with 2 10K SAS drives, right, or 2 15K drives, how many IOPS are we going to be able to push, right? It's somewhere between 150 to 200 IOPS. And that's it. That's all we're going to get on that terminal server before it maxes out. And that kind of makes sense, because when you start thinking about, well, how many IOPS does a user take, while we really didn't think about it, after we did some testing, we came to the realization that, oh, hey, it's about 3 IOPS per user. That's the average of what a XenApp user or a terminal server user takes up, about 3 IOPS. So if I've got about 50 users on the box, I'm chewing up about 150 IOPS. Hence why all of a sudden my RAID 1 disks can no longer support anything past 50 users. But if we put the battery-backed write cache on there and we tuned the server properly, could we go past 50 users on a terminal server? How many people had more than 50 users on their terminal servers? No problem, right? If you tuned them properly, you could. So what was it that allowed us to do that? That was putting that write cache. So if you wanted to go beyond 40 or 50 users, you had to have a write cache on your terminal servers in order to be able to do that. Now, taking a look at the servers back then, if you're using a 32-bit OS, right, you probably ended up running out of kernel memory somewhere. So even if you put the write cache on the server, as soon as you hit 70 users, all of a sudden kernel memory started to be depleted, and you weren't going much beyond that. But you were able to support more users than the IOPS of those disks could theoretically support. Now with proper tuning, even on a 32-bit OS, I had customers where we took them up to 100 users, no problem. And you could tune to your heart's content, but if you tried to go over 100 users on 32-bit, you're definitely playing with fire, right? The server's going to crash eventually. But we could run 100 users on a tuned server. Those users would be chewing up at least 300 IOPS, and the 2 10K SAS disks would be supporting 150. So it really shows you that from that IOPS perspective, that cache really is king. It really does skew the number of how many IOPS you're going to be able to support in the system. Now, when tuning the cache, we always recommended on a terminal server that we should set that RAID card to 100% cache for writes. Right? That was always the recommendation. Some people did 75 write, 25 read, but it was really those write operations. It's the write operations that end up bringing the disk subsystem to its knees. And so that's what we need to try and speed up the most.
Quick poll, who actually knew that we recommended 100 writes, 0 reads? And who's actually doing that? Yep, because that got actually published in some old Citrix consulting stuff I think we did 10 years ago by mistake. But there's white papers out there by HP, Citrix, we've done all of our own testing in the field. Always, always,
On a
100,
terminal
0.
server, you're going to get better performance if you give it 100% right. And we'll talk about this a little later, because when PVS comes into play, OSs use system cache to cache all the reads. So when an operating Windows reads a file, it puts it in memory. It doesn't have to reread it. So the Windows operating system itself has a built-in read cache. It uses the system cache RAM to do that. But it doesn't have a built-in write cache. Right? It relies on the disk subsystem because it doesn't want to put data at risk. So the other interesting thing is right about 2006, 2007, that's when we started to see the first 64-bit servers come into play. Right? This is right before virtualization started to become popular. And I actually did some projects with customers where we did Windows Server 2003 x64 edition on the same hardware profiles. So we're talking 2U boxes. Sometimes we do the 4-socket systems. And in those systems, there was never more than 3 or 4 disks. It was typically in a RAID 5 array, which RAID 5, as Nick brought out, has a penalty to it. So with RAID 5, those disk subsystems were pushing maybe 300 IOPS. But we had a write cache on the RAID card inside those servers. And how many users were we pushing? And some of the scalability tests that I was doing was comfortably getting north of 200 users, 200, 220 sessions on Windows x64 before we actually started pushing the limits of memory and CPU on the box. So 200 users on local storage that supports 300 IOPS, at 200 users times 3 IOPS per user, we theoretically required 600 IOPS. But the disk subsystem of those physical servers only supported 300, and everything ran just fine. And that's really because of that cache. So how much difference can caching make? In a recent test that we had run, we had 2 15K SAS disks set up in a RAID 1 mirror. So that meant we could get about 200 IOPS out of those disks. So we used the IO meter, ran some sustained tests where we were firing away 4K random write IOPS at those disk subsystems. Now, this is where latency comes into play, and I think Nick is going to talk about this a little bit more. The question in the back?
What was the size of your test file, Brian? That can really influence the results you're getting, especially if it's less than you had a 1 gig.
I can look.
I'm not sure, but we'll look that up. We'll look that up for you. But we were getting, in order to stick at about 2 milliseconds of latency, right? Which if you're sub 2, you're going to be able to probably maintain some acceptable performance. We would get 200 IOPS, which is what we would expect out of that RAID array. But with the battery-backed write cache, we were able to push 800 IOPS towards that array. So really the cache is what made that difference. Now there does come a point in time where you can have all the cache in the world. Eventually that data's got to get written to the disks, right? So I can't go put a 1 terabyte cache on top of 2 drives and expect to get bazillions of IOPS. Yeah, if I wrote a small file maybe, but you can't sustain it. So eventually you do overrun what the disk subsystem can do, but that cache levels out those peaks. And if you ever look at like a terminal server workload, or even a VDI workload for that matter, the IOPS are kind of, a lot of times it's sort of chatty, right? You get these peaks. So if you can level out those peaks, which is what the cache will do for you, you'll smooth things out. So, but this is why on a terminal server, we never really had IOPS issues as long as we had a RAID card that had a write cache on it, right? Because we were able to push more IOPS to that disk subsystem than it theoretically could support. So why have things changed? When we look at it, and we look at the VDI profile, instead of doing local storage, which actually, it's interesting, you can do local storage with VDI. It's a total conversation for probably a different session. We got a lot of customers actually circling back around thinking, maybe I should just buy hypervisors and load up some local storage and put some cards in there to handle that caching. But the initial thought for most customers was, we're moving to a VDI workload, we're moving to virtualization, that must sit on the SAN. So we have to move all that information. All those virtual machines go to the SAN. They don't go to local storage anymore. So that was kind of a paradigm shift. Instead of local storage, we're going to be using SAN storage. Traditionally, before virtualization, before VDI, what kind of workloads, if you had SANs in your environment or your customer's environment, what kind of workload typically sat on the SAN? Yeah, databases, server workloads, a lot of databases. People put their Exchange on there. People will put their SQL servers on there, right? So those things, those workload profiles were much more read intensive, right? When you look at a database, it depends on what kind of database, of course, but you'll see a lot more read activity coming off the SAN than you do write activity. And the SANs typically were tuned to give you that really excellent, fast read performance. But when we started looking at, moving terminal server workloads and VDI workloads over onto the SAN, that's a different kind of workload. A terminal server, it might be a 50-50 from a read-write perspective. And actually, if you have enough memory in your terminal server and you have enough system cache, over time, your terminal server will do about 80% writes and about 20% reads at most. Because eventually, if the server has enough memory, it reads all the OS and application files into RAM, and now the only thing that's being written are all the user profiles and the temp files and the other things. So over time, the workloads shift to become much more write-intensive than they are read-intensive. And that was really kind of a paradigm shift, I think, for a lot of the SAN vendors as well, right? So instead of having loads that were optimized for reads, we need to have SANs that are optimized for writes. Completely different kind of profile. The other thing that really kind of changed this around is with PVS, we accelerated the writes, right? The amount of writes that we're pushing to the SAN even more. And in most PVS environments, if you're properly tuned, you'll probably notice it could be as high as 96% of all of the I/O that is going to the SAN on behalf of the virtual machines will be random writes, 4 to 8K random writes being fired at the SAN. And why is that? Why with PVS are we sending only write operations to the SAN and no more reads? The reads are coming over the network, and ultimately the PVS is pulling those reads from memory, right? Another little tidbit, the PVS SCSI driver, when we talk about block sizes and optimizing block sizes, when we're using PVS in our VMs, it limits block size to 32K, and typically 4 to 8 is what we usually see. Now, when the PVS server reads the vDisk, it reads that master gold image, it puts all those blocks into system cache RAM. And we're not doing anything magical with PVS. We didn't build our own cool caching engine. All we did is let Windows do its natural thing. When you read a file, Windows puts it in memory. Plain and simple. So when the PVS server reads the blocks of data for a virtual machine to read and boot or whatever is being requested from that virtual machine, the PVS server reads the file, puts it in memory. Then when all the targets boot up and make a read request, it's a memory over the network operation. So we're going memory, network, memory, network, memory, network. All of our I/O in a PVS perspective from a read operation is a memory to a network operation. So there is no more read operations going to the SAN, which means your SAN needs to be, you need to expect that you're going to be pushing well over 90% write operations and write operations only. So here's a graph of a real-world scenario where this was the LUN that held the PVS vDisk files. The blue line are read operations. The right line is some write operations, and the green line is the two combined. What do we notice about read operations to the PVS line? You see a little spike early in the day, in the very beginning, right? So some new machines had probably booted up. Maybe that was a new vDisk that got rolled out. So the PVS server has a few reads, Once that vdisk is in memory, there's no more. The reads sort of flatline off, and there's very few read operations coming from the LUN hosting the PBS servers. So that LUN hosting all the PBS servers where all those vdisks sits, there's nothing going on. What is the write activity to the PBS LUN? Well, it's one of two things. It's either a virtual machine booted up and had to fall back to cache on server, right, to send its write operations back to the server, or it's somebody updating a vdisk, right? When you make a change to the PBS vdisk, of course, you're writing to the PBS LUN to do that. But from a read perspective, absolutely nothing going on. And this is important to know because you should not be wasting your money carving out an SSD LUN for your PBS servers. And I see customers do this. They're like, yeah, we carved out a LUN, it's tier 1, it's all on SSDs, it's going to be super fast, the PBS's disk store is lightning quick. I'm like, why'd you do that? It doesn't need to be lightning quick. I could pull out a cheap little flash drive, one of the $10 ones that you buy at Best Buy. I could plug it into the PBS server. I could make that my vdisk store, and it would perform just fine as long as the PBS server has the proper amount of RAM. Because the PBS server will read the file one time, put it in memory, call it a day.
And not even that. I mean, you can use cheap SATA drives like from Best Buy.
Exactly.
Right? We don't care about the disk speeds.
So during your update processes, yes, you are going to be writing information to the LUN. But how often does that happen, right? Now, again, I wouldn't go out and use a flash drive from Best Buy, but a standard LUN that you carve off on the regular storage for all the other servers is going to be more than adequate. More than adequate. And you're right, it's all sequential I/O. When you're writing out that new vdisk, it is a beautiful sequential write operation. It can go very fast.
Can you quickly talk about how things work on the MCS side?
Sure. So
Yeah, go ahead. But I'll show you a profile later.
He's
with
actually
MCS,
got some data coming up in a few slides on it. But essentially, in the MCS world, there's a lot more reads, right? Because the PVS isn't sitting in the middle, acting as a giant read cache. So with MCS, we have to figure out a way to cache those read operations, and that's where a lot of times, something like a Zen server and telecache could come into play, or looking to the SAN vendors, making sure that the caching on the SAN is properly configured so that those reads can get cached at the SAN level.
So this is, if your vdisk is on a network share, Windows doesn't cache.
This was a LUN. These were a physical LUN hosting all the PBS volumes. You can use a CIF share, right, to host the PBS vdisk store. There are a few caveats around that. One, you want to make sure the CIF share is highly available. We actually, and I'm in the middle of working with NetApp on this right now. We've had an issue where if the NetApp volume failed over, right, if there was a cluster failover on NetApp, that sometimes our stream service would not be so happy. But
My point is, if you have your vdisks on, if you have a bunch of
You're talking like NFS and CIF, so it doesn't cache by default.
right.
Yeah, but we can make it cache.
Well, we can make it cache it. I actually wrote a blog article.
We force it to cache.
Yeah, there's a few registry keys you flip on the PVS side, and the PVS server will read from the network share, and it will absolutely cache everything. No problems.
It's co-
VDS depends on Windows to cache.
Always.
Right.
Always.
But
Yeah.
we're tweaking like Windows registry keys, like
Yep.
opportunistic locking is the big one.
And
We
Windows
disable that.
caches data from network shares. Absolutely. You open a file from your home directory, that file gets put in your system cache.
But you're
fully
spot on.
cached.
I mean, you're right. Point
Yeah.
taken. It's a valid point.
Yeah.
So if you're using a block-based protocol, fiber channel iSCSI, or local storage,
Yeah.
right, to host your vDIS on PVS, it'll inherently cache because it sees it as a local drive, D drive, Z drive, whatever.
Yep.
If you're using NFS or CIFS, it's a whack, UNC path, whatever, it's remote. Windows says, oh, that's a remote share. I got to go get the latest copy of that every time, even though it's sitting in memory and you have it.
There's
That's
just-
by design. That's a feature.
There's opportunistic locking keys.
But we just tweak that and
that you
make it cache.
tweak, and it turns on the caching because they're read-only files. So but we can totally cache from CIFS. Yep.
This kind of doesn't really go, things change.
Not at all. No difference. In fact, I hope your PVS servers are virtual machines. Because if you put PVS on a physical piece of hardware, you just wasted a lot of money. So PVS should be virtual, should be a VM. Maybe it stores a VMDK file provided by the hypervisor, in which case it's block, it caches natively. Maybe you put the store on an NFS or a CIFS volume, in which case, as long as you tune the registry keys, which I have a whole blog article that I wrote on tuning CIFS for PVS, as long as you tune those registry keys, it'll cache perfectly. Virtual PVSs, though, there's absolutely no reason to do a physical PVS unless you like to waste money.
If you Google CIF stores PVS, it'll probably be the first hit.
Yeah.
If you want to check it out, get those keys.
Yeah, I got customer, and I actually wrote a blog article on virtual PVS, a real-world example, where I actually have some screenshots from the customer's environment showing all virtual PVSs. In that instance, we had over 1,500 targets booted from, that customer had 8,000 active targets booted, and all the PVSs were virtual, doing about 1,500 per PVS. We actually pushed them up to 3,000 active Windows 7 targets booted from a single virtual PVS server. We had no issues with it running. When we did have a few issues when it would fail, and those 3,000 targets would get jettisoned off and have to go connect to another PVS server. We had a few issues then. We actually put some patches out to our stream service to try and stabilize that. But from a load perspective, there's no reason a virtual PVS can't push the load. So what happens with write operations and read operations to the LUN that hosts the actual virtual machine, so where the write cache is going to be. So I've got a Windows 7 VM. It's got a disk provided by the hypervisor, and my C drive writes are going to go to that disk. So what happens in a PVS environment to the LUN that's hosting all those VMs? Well, this is another screenshot of that. And again, you're going to see the same type of profile. Blue line is reads, the red line is write, and green is them combined. Almost all of the IOPS being fired at that LUN, write operations. Hardly any read operations. It's just very few read operations that ever go to that LUN. And you might think, why? I mean, yeah, a user might create a temp file, or the user might download and create temporary internet files, or they're going to load their profile. Yeah, I got it. They're writing a lot of data to the C drive. But don't they read that data? Don't you work with the files that get cached onto your C drive or inside your profile? Absolutely you do. The answer is system cache within the Windows 7 operating system is caching all those reads. So when you go out to the network share and you download your profile, or you create a temporary file in the temp directory on the C drive, as long as you have enough memory in your Windows 7 OS, you will never reread it. You will create it. It could be a 20 meg file. You create it, you dump it in the C drive, you close it, you wait 2 hours, you come back, you double click it, you reopen it. There are no read operations that get fired off at the disk because that file is still sitting in system cache memory of the Windows OS. The Windows OS will use every bit of free memory to do read caching of all the files that it ever touches off of the hard disk. So because of Windows native, and this is what makes PVS successful, but because of that, this is why VMs in a PVS type world, they don't read from the write cache LUN. They write their files to it. Occasionally they have to reread from it. Why? Well, because you can't keep every file you've ever read in memory. Eventually, right, it's a cache buffer. You know, if it hasn't been used, it gets moved out to put something new in. So if you are low on memory inside your Windows 7 target, you might have to go back to that write cache LUN and reread some of those files if they get called again. And that's why you see a few of those spikes. That's probably what's happening with those users. They've used up most of their memory. Now they're reading a file again that they had previously written to the C drive, and we got to actually go back to the LUN to reread it. But that's minuscule in comparison to the big picture. It's really just write operations that we have to worry about in a VDI world.
Yeah, and this was that graph there was that 96%
Yeah.
writes. That's the numbers behind that in the steady state, which we'll talk about, I think, in a slide here too. Because I was saying the gentleman made a good point about, what happens if you like update a VDIS. Yeah, totally. But, we're talking steady state. For the most part, there's always, there's going to be little exceptions. And there's different I/O profiles in the, the boot, log on, log off. We'll talk about that in a minute. Can't just discount it, but the majority of the time we're talking steady state.
When we talk about IOPS and steady state IOPS, which when you were looking at those graphs, that was over a whole day. You might have saw in the beginning of the day there were a few spikes, but then things leveled off. But for the most part, that was steady state. The I/O profile going to those lines was fairly consistent, right? And that's typically how you'll see it once you get into that steady state. Now there are three different kinds of phases when we're talking about VDI, right? We got the boot phase, we got the so-called dreaded logon storm phase, right? And then the initial phase where users are starting up their apps. And then once everybody's on and logged into their system, then you hit that steady state point. You do have to understand that the I/O profile between those various phases is different, right? So we talk about 90% write operations in the steady state. But if you narrow in on that window at the very beginning, that's not going to be the I/O profile, right? During the boot phase, what are we doing? We've got to boot the OS. That could be a lot more reads, right? Maybe the PVS, it's a new vDisk, it wasn't cached. Maybe I'm using MCS and I don't have PVS. So I've got to go back to the storage and read the files to boot that OS. So bootings, you'll get a much heavier read operation. Same thing in the logon phase, right? In the logon phase, you're also going to get a lot more reads with a fair mix of writes because you got the profile coming down. You got the user starting to read new apps that need to be cached. So during different phases, there are different I/O profiles. The reason you really only need to worry about steady state, though, why steady state in the end should be the only thing you worry about, is because the boot phase, we know how to mitigate that, right? You should not be, if your users come to work and they're using VDI and they start their shift at 8, don't boot their machines at 7:50 in the morning, right? You boot their machines at like 4 a.m. You boot them at 5 a.m. So you do have a big read, big boot I/O storm, but it happens at 5 a.m. when nobody's in the building and nobody's using the data center. So you don't care. It doesn't matter. So the boot phase should never be an issue. If it is, you haven't configured your power management settings correctly for your virtual machines. Now, what about the logon storm? This one can be an issue, but I would argue it should not be an issue at all. And in fact, if you configure your profiles correctly, and you configure your folder redirection policies correctly, the logon phase can sometimes even be a smaller I/O footprint than the steady state phase, right? And that might be hard to believe, but if you come to Nick's and I's session tomorrow where we talk about folder redirection and properly doing folder redirection, I have real world data where I will show you that in a properly configured environment, the logon times produce less I/O than the steady state. Because if profiles and folder redirection are done correctly, logons don't do anything. They're just a little blip on the radar and you don't got to worry about it. But you do have to configure your profiles and your folder redirection correctly, or the logon storm phase could end up burning you pretty bad. And with that, I'm going to hand it back over to Nick.
And by the way, that graph there you saw was courtesy Project VRC Phase 3. And then I think Jim's made a couple of comments, but what was it, a couple of years ago, you published that white paper on Windows 7? So if you haven't seen that one, check it out. Again, Google it. Windows 7, IOPS, it'll probably come up, right? But Jim and the VRC guys in Phase 3, basically, they looked at booting Windows 7 and the different life cycle of a VM. And Dan mentioned talking about the boot, the log on. Well, there's first application launches, second loops, log off, idle. So there's 5, 6 maybe phases there. And it was kind of enlightening. So if you haven't seen that, or you're wondering like more details behind this right here and how how Windows actually does that stuff, definitely check out those resources. Really good stuff. All right, how storage vendors dupe you. Only one storage vendor in the room? Really? Should I even ask you who you work for? No, that'd be bad.
You named them.
Okay.
I work for all of them.
Okay, yeah, small world, right? Just kind of like consulting. Let's see if this works. All right, it works again. All right, so storage benchmarking. Yeah, so like I said, they can say anything. 1 million, 500K. I'll show you some examples, and they always come with a nice, pretty press release, right? That says, Hitachi just broke the world record, 4.2 million IOPS. And you're like, what? And you read the report and it's like, well, yeah, and like, it's actually 200K IOPS at like 1 millisecond latency. So it's 4 million, 200K. Pretty close. Like I said earlier, they're usually best case scenario, sort of marketing-ish numbers. That's a typical profile, right? You're gonna have a large block size, a high mix of read, sequential I/O versus random writes. Caching is usually going to be enabled. Some of these tests I was looking, there's like 24 nodes and there's 256 gigs of cache and it's tuned for, it's like, gee, well, yeah, if you do all that and you serve everything from cache, yeah, you can get 1 trillion billion million IOPS, sure. And then we'll look at the latency too. So yeah, they're going to play to their strengths, and like I said, it's always really difficult when you're reading like the NetApp or the HP or the Hitachi study itself to get apples to apples. I pulled 5 or 6 examples you'll see here. Every single one of them was different. The only way you can get kind of true apples to apples is if you go to like the Storage Performance Council and look at like the spec stuff. But again, their profile is, for the SPC like 1 IOPS, it's not indicative of a real VDI load. So it's like we just can't win. So yeah, let's take a look from some of your favorites. So let's first look at our friends at EMC. So this is the array was a VNX 5700. The quote here was 497,000 IOPS. And then, like I said, oh, by the way, so all these, if you want to look at the actual tests themselves, I have URLs from every study, from every report in the slide notes, so if you just want to check them out later. But here's, the press release. It's, 49% faster than HP, 23% faster than IBM, and then the next month, the other vendor comes out and publishes the exact same thing. It's kind of like what XenServer and VMware used to do. It's like 5 users more per box, and there's like 4 users more per box. Like, who cares? So the variables here, auto-tiering, so they had the fast and fast VP enabled. Caching was enabled. In this case, they used 10 gigs, and they were using RAID 5. So if you actually dig into the test, it was actually only 100K IOPS at 1 millisecond in latency, and it was that 497K number they quoted was actually at 3.3 milliseconds. So and that's the difference between having a good user experience and maybe a poor user experience. How often have you seen your VDI environment where, XenDesktop or View, and they're sitting there looking at a frozen screen or an hourglass, and you're like, what's going on? I have available CPU and memory. Everything looks great. The network looks fantastic. The network guys can't say anything. It's like, yeah, your disk latency is like, 25 milliseconds. That's how it manifests itself. You're looking at a frozen screen. Yep. So, and then the other thing to mention about latency is, different applications have different susceptibility to latency. That's really important to understand. So like a database application, especially with write I/O, it might expect a response or require a response in sub 4 milliseconds we've seen in the field. If it doesn't get that response, it might just hiccup, crash. Lots of fun things happen. If it's sequential read I/O, maybe we can go higher, 10, 20 milliseconds and live with it. So, and it depends on the application, but I can tell you XenDesktop, View, these VDI workloads, we want to see sub 2 milliseconds. That's where we want to be. The block size, so this one I actually pulled from the SPC. They just have the famous auto here, and then if you dig into it, you can see what it is, but they don't, right off the bat, it's kind of unknown. Yeah, let's look at, how about NetApp? So here's a 6,000, fast series. IOPS quote, 1.5 million IOPS. So you look into this. So some of the variables here, so they have flash cache, for some of the reads, we can turn that baby on. In this case, 512 gig cache in each of the 24 nodes. I mean, just like, who's doing it? Like, it's ridiculous. Sure, it's like, yeah, it's great. They're using RAID DP, their RAID technology, but I mean, it's just insane. And then when you actually dig into it, it was, the 1.5 million was at 4.5 milliseconds. So again, it's not a good test. That's a bad number. We shouldn't be quoting numbers like that. It's only 500K IOPS. And,
It's less than half the infrastructure.
Right. Yeah, exactly. It's ridiculous. So, and I don't want to, pick on NetApp. I'm picking on all of them, obviously. We're storage and hardware agnostic at Citrix, right? But, a real world scenario, one of our really good customers, in the West, they kind of, heard this number, they bought one array, and they had like 7,500 desktops. Well, once we got into it, the array came crashing down to a screaming halt because we were doing 4K random write I/O, and we ended up basically having to buy 3 more. So I mean, it's just That's the kind of stuff that's happening, like if you just take the vendor's word for it. And honestly, it's not just the vendor we can blame, it's partly our fault as the end user too. You got to test. Every workload and I/O profile is different. You have got to test. I mean, that's what it boils down to. Now, block size, again here, unknown. It's like, that's like, how do you even come up with these numbers and you don't even publish the friggin' block or whatever? Oh, they know it. They just don't want to tell you. Yeah, 128K. Yeah, we know it. HP, so here's like a mid-range, a 3-par 7400, smaller quote here, 258K. But I just want to show you different examples. In this case, caching enabled. So as you've already seen, caching different. Some are mirrored, some are 16 gig, 10 gig, 128 gig. I mean, it's all over the map, right? And this one was actually a good test. So this is one I wanted to highlight where I thought, HP did a good job.
Real numbers.
Right, real numbers. So that 258K was actually at like sub 1 millisecond, or right at 1 millisecond, I think it was. So that's good stuff. Not good stuff is the 70% reads and 30% writes. So great, if we're doing database applications or something like that where it's reading all day long and 80% reads, that's a good profile. But for anything we're doing in this Citrix VMware virtualization world that we live in, it's a terrible profile. So it might be 50K, and that's kind of the stuff we're dealing with. Again, block size unknown. How about Hitachi? So this is actually the Blue Arc product. It's HNAS 3090. They didn't actually. This one was interesting. They didn't even give an IOPS number. They published all this stuff, and I pasted this. They actually created their own VDI IO mark to come up with their own profile, which is good. I think that's great. It's better, but they actually didn't even quote a number. And then the other thing I thought was cool here is some of those techniques that vendors use to really bump up their numbers big time, like read ahead, caching, they disabled them in this test. So I thought that was also great. When you do your own test, you should turn this stuff on and off, like Dan and I were doing with the battery back write cache. What is the difference? What is it actually? How does it impact it? That's stuff you should be doing. The read-write ratio, again, better. I like what I'm seeing here, that 40-60. It's not as, again, maybe this is a great test, though, for MCS, which we'll talk about in a little bit here. They actually did variable I/O size, and they published what they did, but about 70% were 4K. So again, good stuff there. Yeah, so that was actually pretty good overall. So Hitachi here, I have a bad and a good, because they're all over the map. So here's a USPV, the IOPS quote, 4 million IOPS. This is, it's down there at the bottom, 4 million IOs per second. So that sounds great. Then I actually dug in and I found the same array, and I went to the Storage Performance Council, and so they tested the SPC1 IOPS benchmark here. It's 200K, 4 million versus 200K. That's a huge freaking difference. Talking about buying maybe 10 more of these arrays or something to support a workload, of that nature. How about our friends over there? So now I'm done with the storage vendors. Let's maybe talk about our friends over at VMware. And by the way, we're guilty of this too. Like I was looking at our own Citrix internal solutions lab testing and our engineering testing, and we're using ridiculous block size numbers.
Never believe those numbers.
Yeah, we don't publish like our throughput. It's just so we're all guilty of it. I don't want to pick on VMware here. But this one was interesting. So the bottom there, it says vSphere can easily support 1 million IO. So this is a single vSphere 5 host, and they're saying they can do 1 million IOPS. So I looked at it, I read the white paper, 100% random, good, 100% reads, no writes. It's like, sure. We could serve everything from cache. It's just completely bogus. And then the block size was actually small, so they're using 512 bytes, 4K, 8K. So that was good, but it's just 100% reads, it totally invalidates the whole test. So I was saying it's probably more about 200K, 100K with random writes. Here's a test I liked though. So this is actually one of their latest ones. They just did with 5.1, and the array was a VNX 7500. And so what they were trying to basically prove here was, could they get near like line speed or wire speed? They were testing out the 16 gig fiber channel HBAs. And so actually on this one was awesome. The IOPS quote, they didn't give you a number, which I thought was great. So if anything else, like I said, talk throughput, and that's better than nothing. Throughput is, at least we can understand that a little bit. On IOPS numbers is kind of meaningless. So the 1550 megabytes per second, again, that's really close to that 16 gig, that HBA, right? So that's what they were going for. What did they actually use though? So as you can see there, they used variable block sizes, which is good. a single worker sequential I/O. So, you know, we almost got it right, but then there's no random I/O. So, again, it kind of invalidates the test. But again, I thought that one was better. I would like to see graphs that don't have raw IOPS numbers. I'd like to see throughput.
There's a slight difference here in VMware's defense, though, because they're really talking about what the hypervisor can suck in.
Yep. Yeah. I mean, it's a different. Yeah, it's a different test than like the arrays and the looking at it that way. But yeah.
So I'm not sure I kind of agree with you about throughput. Throughput's only predictable, predictable block size. Right?
Yeah, and we talked about that earlier. So yeah, point taken. But
And especially when you relate back to Windows, so Windows 7 and Windows 8 has got a maximum block size of 1 meg.
yep.
So you'll actually have very few IOs at that block size, but it will actually account for a large amount of the throughput. So it really sort of skews your results if you talk about Windows and throughput and how to relate that to IOs. So I think it's difficult when you talk about Windows to really say that throughput is the thing you should be watching.
Yep. Would you agree though that throughput's a better measurement than IOPS itself, a number?
So IOPS, if it's honest, is absolutely fine. But you're right.
I mean, how do you?
Vendors are not honest.
Yeah. Most I mean, they're both bad without clarifying info. I think we'll agree there. But I mean, I think I'd argue that at least throughput and bandwidth, I think it's something that a storage person can understand a little bit better than some nebulous IOPS number. I don't know. I mean, I guess without info, they're both nebulous.
Yeah.
But yeah.
Buyer beware.
Yeah, exactly. we could talk all day about that. How about some real world stuff? So I just want to show you now just some of our customers. I just kind of handpicked a few here, but I wanted to show you like the I/O profile in the steady state production environment. So first one's a large hospital. They're using Zen Desktop with PVS on Zen Server on UCS. About 1,500 VMs running daily, and they have a VSP. So fiber channel, RAID 5, they do use the Hitachi dynamic tiering, the HDT stuff, and 110 gigs of cache. So these are monsters, right? Like a VMAX. I mean, these things just have oodles of cache. So the stats, and this one was so kind of interesting. So writes, it was 91%, and then reads 9%. The average block size, again, 4K. It's very typical right here, all this stuff of a PVS workload. I have average latency there and peak latency, the average IOPS and peak average IOPS just for fun. But I wanted to show the IOPS there. Again, I said I wasn't going to talk about it, and here I am showing these numbers. But I just want to demonstrate that this is about as good as it ever gets. This customer basically had the complete utopia, complete Zen app integration, which means they basically had a Windows 7 image with nothing in it. So yeah, the IOPS is basically going to be that 6 to 10 number that we quote for basically Windows 7 doing nothing. Or maybe it has Office or IE, just the basic stuff.
Any idea what that array costs?
I don't know. A lot.
$5.
$2 million? Yeah, something like that's what I guess.
So why does, as a consultant, why recommend such customers to use shared storage?
What's that?
Why should they use shared storage?
Oh, the 10 Dan session, I think Thursday. Dan Brinkman's going to talk about local storage.
Yeah.
And Dan kind of hinted at it too, but
It really does.
you don't need to.
Honestly, I think it makes a lot of sense to start thinking about, let's put the VDI workloads back on local storage on the servers.
Well,
in certain circumstances.
Yep.
Certain circumstances.
Well, and the improvements to the hypervisor, right? Which I'm sure there's other sessions on BriForum to talk about what VMware's doing with CBRC, Hyper-V is doing the same thing, Zen Server,
Yep.
Telecache.
It's not really shared and local, it's overly expensive and cheap, and there are things in between
Sure.
that might still be shared, but don't have these price tags.
Yeah.
True.
I think it was like 2 years ago, right? Right before that BriForum that we had the epic debate out there, Brian Madden and Ron, and I mean, everybody was chiming in, right? The local storage versus shared storage, and it was NetApp firing away, Ron, and back and forth. I mean, that's literally an epic debate, and there's pros and cons.
Yep.
Yeah.
As you mentioned Epic, this is probably because Epic, the company, has certified it with XP, and you have to run it on that platform. You cannot run it as local storage.
Yeah, there's fun things like that play into it. Yeah, we're working with those guys. Yeah, SAP, Epic, Cerner. I mean, there's yeah, definitely.
Yep.
Let's show you the next one here. So this is another customer I have in the West here. This a semiconductor, a global company. I wanted to show you just a little bit different because these guys there's 400 VMs in production, but 20% are dedicated. So in the sense that no PVS. So that changes things a little bit. And this was a Symmetrix VMAX. Again, how much does it cost? Another one of these arrays that are just astronomical, right? I can't even, with all the features and stuff, you know, they sell you on top of it, a couple million. Stats, so this one was cool because we actually broke it down into what was random and what was sequential. So you can kind of do the math there, but you know, overall I think it was, yeah, about 75% writes. And then you can see the difference between, you know, how much are actually random versus sequential. So overall it's like 85-15 it looks like, sequential versus random. So kind of interesting to see it that way. The thing that skewed this a little bit was we also had some XenApp VMs on this LUN, almost by mistake with this customer. We found that during the health check. So that was kind of bad, but that's why it skewed the number into like that 75-25 range, even though we had PVS. The other thing that skewed it was with dedicated desktops. So if we're just using, you know, just straight up dedicated desktops, assigned desktops, or like we're using MCS or link clones in a view environment, it also takes that number down. It's that sliding thing from maybe the 90-10, 80-20, down to closer to 50-50. And I'll show you that on the next slide. Oh, just for fun again, average IOPS for Zen desktop VMs, so 29 here. So a lot different from the 9 I think we saw on the last slide. And this was a customer that kind of, you know, one of these customers that rushed into VDI, all their apps are in the image. So no utopia, no layers of cake here, right? It's just slam it all in, fast, cheap VDI, do it, go, got a deadline to hit. The last one was, this is one of our largest MCS installs in the world. And we don't have a lot of these, but that's why I had to do some digging to find this data. But I wanted to show you, I think it's representative of, you know, the gentleman asked the question, you know, how does MCS compare? So this is with a NetApp, you know, 3000 series array. So yeah, it was, in the steady state again, it was about 55-45. And we did some internal testing about, you know, maybe two and a half years ago in our own lab, and it was like 51-49. So it's very, very close to that in a steady state. And you're right, and so there it is. I mean, without PVS, and if you're using MCS or like link clones, you're going to see a profile like that, about 50-50. So, you know, again, your storage vendors, they should not be selling you storage unless they know your I/O profile. So I mean, we've tried to do all this like cross, you know, education and collaboration and stuff between the storage vendors. They still don't seem to, you know, I mean, some do, of course, but some don't, and they sell you storage, you know, and then you're kind of up a creek because they don't know, you know, if you're using MCS versus PVS and how that shifts things. You know, 50-50 versus 90-10 is vastly different for what you should be buying or planning for, right? Yeah, so that's why it's so high compared to PVS, just because PVS. And then PVS, again, is caching all those read IOPS, as Dan talked about. So we don't have that with MCS, link clones. Those read IOPS are going somewhere, and those somewhere are being, you know, hit by the hypervisor local storage, the array in this case, whatever. The average block size, 8K. It's, you know, and as you saw on the last slide with PVS, the median block size is always like 4 and 8. That's what it's generating the most of, but it was interesting, 8 here with MCS. You got the latency numbers there. And then, yeah, anyone know, so the IOPS 15 and 18 for the average and the peak IOPS, anyone know how that might compare to PVS? Anyone done some PVS versus MCS testing? Yes. You shouldn't, you can't answer that.
I did a test on it yesterday.
Oh yeah, what did you find?
So, it's obvious that, as you say, you're going to get your reads over the network from PVS, but I found that you got, in steady state, MCS was 8% worse than writes and 21% worse in total amount of reads in
Right.
steady state.
What was it, 80%? 8.
So 9% worse if you just consider writes,
Yeah.
and 21% worse if you consider the extra writes and reads from MCS in steady state.
Right.
Yeah. Obviously, if you consider boot or application launch, then that's going to be completely different.
Yeah.
But I think that essentially what PVS is doing is providing a static read cache.
Yeah, it's like just a buffer
It's
for
a giant
read.
read cache. That's the beauty of PVS.
Well, the thing
Yeah.
is that you've got a whole load of bastard infrastructure to provide a static read cache. So you've got PIC, I mean, or BDM, whatever, you've got your SQL server, you've got the streaming service, you've got the hosting service, you've got your PDS, you've got all of this shit.
So complicated. Virtualize it.
Static read caches are all over your infrastructure. As you say, read caches are easy, right?
Yep.
Windows has got one, Raven cards have got one, your hard drive's got one, your SAN's got one, they're everywhere.
Yep.
So why create this whole load of infrastructure for a static read cache when you have loads of them anyway?
I mean, I'll add to it too, we're also still doing read-write balance, a little bit more balance. And back to your slide where they got that 6 times write down per read.
Yeah.
When you look at a VDI workload and the the amount of reads that it takes to get that OS up, get those users logged in, and get those applications launched, it's a massive amount of reads. You need a cache somewhere to handle that. So, I mean, I would argue long-term, PVS, I mean, I love the technology. I think it's the best technology for delivering VDI today. All of my biggest customers use it. 20,000, 30,000, 50,000 seat deployments. None of them could be successful without PVS. But PVS is not the best place to do that. The hypervisor should be doing it, right? VMware's starting to move there with the, what do they call it, the content-based read cache
CBRC,
for link close, right? Microsoft is now doing it on clustered shared volumes on Hyper-V 2012. Microsoft's introducing it. We tried to do it with IntelliCache with Zen Server, which, yeah.
We'll talk about that
It's
later.
crap. But everybody knows using PVS for this read cache is not the right architecture. But it works today, and it'll let you scale. I would argue in the next 2 years, we won't be talking a lot about PVS because the hypervisors know that they should be caching it. If I have a VMware server or a Hyper-V server or a Zen server, and it reads one gold image for you're the VM you're booting, you read all the blocks. And now he's booting, and I'm reading the same gold disk. Why does the hypervisor reread that? Why can't we just carve off a little cache? And it doesn't take a lot, 2 gig, 4 gig, 8 gig. On a hypervisor that's got half a terabyte of RAM, you can spare 8 gigs of cache. Let the hypervisor cache that read, and let's cut PVS out of the middle. So long term, that is where it's going to go.
That's definitely right, but you gotta remember PVS isn't just a cache, it's also a machine identity.
That's the other piece. Disk versioning, machine identity, and the ability to get those vDisks across all those different hypervisors with the storage platform is also a challenge that has to be solved. So the hypervisors are fixing the caching issue. They're already basically there. Microsoft is there with 2012. VMware got there with the content-based read cache. Citrix sort of half got there with IntelliCache, but yes, not really. So the hypervisors are getting there. Now it's just how do we manage the gold image across the LUNs, right? And that's coming. It's coming.
Yeah.
So it's not quite there yet, which is why the big customers are doing PVS. And PVS today is still the best solution for large-scale VDI. But again, 2 years from now, I hope that it's not, because that technology should be a native function of the hypervisor.
Yeah,
and it eventually will.
And I know there's been discussion about that, and like Brinkman, I think, has written about that, and I think Jim maybe fired a comment away on maybe that article. But we get it.
Sure.
It is a lot of infrastructure, and that's why we've been saying, like we've written the blogs like virtualize it. Then at least people aren't wasting money on physical servers for a read cache. To your point, it's ridiculous. So that's one thing. Yeah, it's a read cache. It's also an imaging tool, which we still there's other tools and stuff out there to do that. Yeah. But there's also one other point. So the complexity though of PVS is definitely point taken. So I can't tell you. I always say to our customers, PVS, one of our most powerful products. Probably one of the products that people screw up the most, and one that causes the most outages in environments. So even if you design it perfectly, it's like you got to make SQL highly available. Oh, what if there's a SQL deadlock issue? What if the stream service crashes? Well, it's the heart of your infrastructure now, so your whole environment's down. So yeah, we get it. We agree with you, and our roadmap actually will reflect that. You'll see. I think the powers to be understand it. They get it, and we're moving in the right direction.
It'll be replaced eventually.
Yeah.
Cache the memory. You can use server's memory as a write cache and get rid of the you totally run it off of the memory.
Yeah, but I mean, there's other, like we're starting to do that at different layers, like the hypervisor, right? So.
As of today, right? We have a workload.
Okay. All right, so last couple slides here, conclusions, key takeaways. I think we've beaten this to death, but yeah, IOPS numbers by themselves, they suck. Same with throughput numbers, I guess, right? I think we're all in agreement now. They're sort of nebulous. But just ask for that clarifying info. One thing I always, when I get into a discussion with a customer and they're planning for storage, and the vendor's in the room with us and we're working together, I want to make sure that the vendor understands that workload and our I/O profile. It's absolutely critical. So, ask the question, help them understand that a real VDI workload's I/O profile is, 80/20 or 90/10, that the majority of it, is random I/O, that the average block size, 4 to 8K. Once if you're intelligent enough to ask those questions, I think you're going to get a better response back from the storage vendor, I hope. If they say, well, man, I've never heard of that type of profile before, probably look at another storage vendor.
Yep.
Yes, we talked about sustained latency. Of course you saw those. I mean, 1 to 2 milliseconds is where I think that's a really good. I mean, that's where if you can be there, that's great. And as I said, different workloads have different susceptibility to latency. This was the iometer setup. Let me see to Jim's point, how many workers? It doesn't say on there. It's dang, it's the other screenshot. But yeah, I think it's 16. I'll double check. Or is it you're saying it's 1?
So Q gets to 16.
Yeah.
And I usually, because workers is spread,
Yeah, it's like out.
I usually do double the amount of workers than you've got, of course.
Yeah. And that's what I saw in actually most of the tests. So I think people get that much down. That's about it, though. I also saw this NetApp. They have this system performance modeler and their VDI template, and this was pretty good, I thought. So I mean, if anything else, I feel like NetApp kind of got it right. The key things to point out, I guess, here is the right workload estimate. It's 90. So they're using a 9010. They're using an 8K size. So that's a pretty good. That's what they're using in their SPM. So what do I do? Because all this is definitely complicated, and So again, don't let storage vendors code IOPS numbers without the details or clarifying info. Don't just accept IOPS numbers without all the details. Ask for the performance test criteria that backs it up. Don't just look at the press releases and say, oh yeah, Hitachi, 4 million IOPS. Look at the thing, download the white paper, and look at all they usually have, like I said, the majority of the variables published. Sometimes they don't publish like block size or whatever, but usually there's the details are in there. And again, ask how the arrays fare in the real world. Ask these storage vendors, how do they stack up with this type of profile? And last but not least, it's like, don't trust anybody. Do your own testing. You can only, your workload and your profile is going to be different, right? You're going to have probably some mix of PVS, maybe you have some MCS, maybe dedicated desktops, you got some XenApp. You're going to have your own unique read-write ratio, right? Your own unique random to sequential ratio. So that's the only way you really know. And there's lots of fun tools, I've pointed out a few there. References, credit. So yeah, as I mentioned, those slides 21 to 27, I have URLs in there, links if you want to read the storage performance, tests and benchmark white papers there. The VRC Phase 3 white paper where we stole a couple of those screenshots about the steady state. Again, PQR, the Deep Impact VDI and Storage white paper, pulled some stuff out of there. It's always a good one, published a few years ago. I think all you guys know that following Brian Madden. Yeah, and then just some of the other random stuff. All right, so we didn't leave much time for questions like we usually do.
We are actually completely out of time.
Oops.
But the good news is after this next set of sessions, we do have